Okay, please let me know if you can't see the screen, but I'm sharing right now. And if you have questions, feel free to unmute yourself and chat. Let me make sure that I have everything set up. Am I unmuted? Yes. Okay. So I just want to show you guys real quick the GitHub. So the GitHub is where we will have all the slides and notebooks from previous meetings. So as you see on this repository, we have the past 3 meetings, and the links will take you to the slides. So today's slides are here. And yeah, I'll go ahead and get started and present to you guys image recognition with convolutional neural networks. And what image recognition is, it allows you to identify objects in an image and tell you what it is. So here in this on the right, it's like, for example, if you were working with autonomous vehicles, you want to be able to identify like cars, passengers, lights and stuff, and like sidewalks. So as you can see, they have bounding boxes around these cars, and they're telling them they're able to identify if it's an SUV, passenger car, and then here they have a police, and that'll give you information. It'll give the neural network the information and make a decision off of that. But in the end of it, we really just want to identify what's in the image. And so for the agenda, I will explain the problem, which I kind of just touched on just now, and show you guys how computers see images. And then we'll get into the convolutional neural network, which is what we're really trying to discuss today. And then I'll do a code demonstration. And I could also just do the code demonstration from scratch and walk step by step for you guys, or we can just go over it, whatever you guys prefer. But let's
I have a question.
Yes.
Have we already discussed the basics in convolution neural networks?
No, we did not discuss the basics of convolution networks, but we did talk about the multi-layer perceptron, which is, okay, you were here for that?
Yeah, I mean, I was there towards the end.
Okay, cool. Then that's all you need to know.
Okay.
Everything is going to be new for today. All right, so we had the problem of last time when we were discussing multi-layer perceptron is we want to be able to identify if a student was going to be admitted into to graduate school, right? So we looked at 3 features, or actually more than 3 features, but here are 3 examples: their GPA and their GRE score, which is like it's like the SAT for graduates, and then like whether they did research or not. And so those are 3 features, and based off those features, we could kind of tell if they were going to be admitted. Like if you had a high GPA and high GRE score, then yeah, you'll probably get admitted. But in our case, we want to identify if an image is of a dog or a cat. And so this is the problem of image recognition. And in this case, we're looking at 3 like physical features instead. So here we have like whether the image has like, or whether the object in the image has floppy ears or upright ears, right? So if you have floppy ears, then you're probably a dog. And if you have upright ears, that's more of a trait for a cat. And then you can kind of like look at the fur type and you see like I guess cats, they have like longer fur, but that's not always the case. But that's just one thing, and that's just one feature. Sorry, and you can look at a bunch of features, right? Their eyes, maybe their mouths or nose, stuff like that. And so that's the problem. How do we identify these features from an image? So in the multi-layer perceptron, we would just input whether not image, but whether the data point had the GRE score, their GPA score, or did research, right? If we were able to look at an image, right? If we looked at this image per se, and we wrote down 3 things, right? If they had upright ears, or if they had floppy ears, and like the fur type or something, then the multi-layer perceptron could classify that image technically, right? But the problem is the image doesn't tell you this right off the bat. You need to do a couple things, right? You need to actually, first, the human needs to look at the image and write down if the image has upright ears, or the object in the image has upright ears and the fur type and stuff. And we can't do that, right? We want to be able to pass just the image and have the network learn that on itself. Is there any questions there? I don't think there's any questions, so I'm gonna move on. So yes, the images, they're gonna be labeled with cats or dogs, and somehow this network is gonna learn just from reading the image, right? We're not telling it if it has upright ears or if it has floppy ears. We just send it in the image, and the network will output the class. So let's talk about how images are represented in computers. And it's most cases, if you have a black and white image, it's going to be 1 and 0s. And red, green, like RGB images are going to be a little bit different. And I'll show you the end of the PowerPoint. But for now, just understand that image is going to have, let's say, a 32 by 32 image is going to have a 32 by 32 matrix representation. And there can only be 2 possible values, 1 or 0. And 1 will be white and 0 will be black. So like this like smiley face looking image will have, this is what, a 6 by 6 image, right? So there's going to be 6 rows and 6 columns, and either 1 and 0, 1 for white, 0 for black. And so there's a smiley face. And so that's an image. And we were going to pass this as input into a neural network, the convolutional neural network. But first, let's start off by trying to identify an X, right? How will we identify this X? I did say like white was 0 and white was 1 and black was 0, but here it's like 1 and -1. But the whole concept I'm trying to explain is going to be the same. So how do we identify this X, right? We can look at the features of an X, right? There's really 2 main features here. I don't know if you guys, it's not easy. It's not like easy to tell, but if you sit down and look at it, all X's have the same thing. They have this body, right? And they have their legs. So the legs of the X and the body of the X are like the 2 main features we're looking at. So if you wired this to a neuron and you wired this to the neuron, this leg to neuron, and this leg to neuron, and this leg to a neuron, that neuron could tell if it's an X based off whether it has 4 legs and the body. So that will be able to identify if it's an X. And here was a distorted X, and it could do the same thing, right? You just need to look at the legs. So it has the legs here. It's just in different positions. And I'll show you how the convolutional neural network, what it does to deal with distorted images. And it also has a body here. And that's the problem we're trying to solve here. How can the convolutional neural network identify features and pass those features to our multi-layer perceptron, which will make the classification. Right? So I'm just saying that this is the exact same thing I'm just saying, but now here's like a visual representation. We're going to pass this image into this black box, which is going to be the convolutional layer and the pooling layer. This whole thing, think of this black box plus the multi-layer perceptron as the whole convolutional neural network. But there's 2 layers that I will introduce right now that will be the remaining parts of the convolutional neural network, right? Like I said, the problem is how do we learn useful features from an image, right? The useful features can be floppy ears or like upright ears, whatever the object has. So the 2 important questions is that I want you guys to keep in mind while we are going over the rest of the remaining slides is how do we find/extract features, and how do we do the same thing? How do we find and extract features with slightly distorted images? And that's gonna be the importance of the 2 layers. So the 2 layers I'm going to talk about is the convolution layer and the pooling layer. And these are the this with the fully connected layer, which is the multi-layer perceptron, is our whole convolutional neural network. So we pass an image to this, and it will be processed by the convolution layer and then pooling layer, and then pass into the multi-layer perceptron. I'm going to pause there and see if there's any questions from you guys. If you have a question, please unmute yourself. It's a little bit easier to follow any questions there.
So we had briefly just mentioned the neural network would be used after it had gone through the convolution, the pool. But is this convolution itself a neural network, or is this like specific for finding features? Like, what do you say? Like, what are these steps doing?
Mm-hmm. Yeah.
And yeah, like, and is it just like clarifying?
Yeah. So this by itself is, you could think of it as like a subnetwork, right? There are two jobs, right?
Yeah.
Right. The job of the convolution and pooling layers will help us find these features, and I'm going to explain that in the next slides. But the second job is like we need to classify like based off these features, and that was the point I was trying to get back in this slide, right?
Yeah.
If we somehow could tell the multi-layer perceptron this image has floppy ears, upright ears, and fur type, then this will just handle the classification.
I gotcha.
Okay. And that's why I had this black box, right? These black box is going to do the feature extractions and stuff. So yeah, that brings us to the point of the convolution layer, which its job is to extract the features. In the previous example, I talked about floppy ears and upright ears. It will look at the image representation, right, which is a bunch of pixels and represented as a matrix, and it will extract these pixels, and it somehow knows to find the right features to extract. And let me explain now the whole operation. So the layer does a convolution operation on two things. It does it using the input data and this matrix slash what we call a filter. This filter, we do not specify the exact values in the filter. The only thing we specify is the dimensions, so a 3x3 matrix. And this input data is coming straight from our image source or from the previous layer. Is either the image source or the previous layer. So that's the input data. And we do a element-wise multiplication. So if you guys know what element-wise operation or multiplication, it just 1 times 1, 1 times 0, 1 times 1. I'll show you here. So here we have a 5x5 image and a 3x3 filter. So we specify the filter to be 3x3. It could have been 5x5. It's really, I guess, based off what has worked before, but 3x3 is a common one. So first things first. Oh, sorry. One thing I want to mention is the filter. This filter is trying to look for x's. I can see here, there's ones on the diagonals and zeros everywhere else. So it's trying to find x, right? So we place that over, for example, another 3. Let's say there was a 3x3 image that had exactly like this this filter right here, and you did element-wise multiplication. You should get the same thing, right? So just looking for a region that looks like an X. If we were looking for a straight line, you would just have ones down the middle or something. But let me go into the operation. So here it does the element-wise multiply, and then it does pretty much like I wouldn't say it's a dot product, but you add all the values in that the result, right? So here they did 1 times 1, 0 times 1, 1 times 1, 0 times 0, and so on. And then so you end up having 1, 2, 3, 4 values, right, that were matched up with that one. And you add it all and you place 4 there. Then you move it, you slide it over, and you do the same thing with the new window. So this is what we call the window, right? This window is sliding over because the input data is bigger than our filter. We're going to shift the filter over to this new window, and we're going to repeat the same thing, right? But this time you see there's only 3 ones that are matched up to each other. So then you add them, and that's a 3. So ideally, right, if there was an x here, you want a value 5, right? Because that means they're ones matched up on all the ones on the filter. The ones in input data match up with all the ones in the filter. So you slide it over again, and you do the same thing. You do the element-wise multiplication. And as you see here, there's 3 ones that match up. Actually, 4 ones that match up. This one doesn't match up. So you add them all up, and it's 4, right? If this was a 2 or something, then you would have 5, because then you would 2 times 1 would be 2, and you just add up the other 3s. But we're just dealing with 1s and 0s for now, for simplicity. Same thing again. This time you have 1s that match up. This one and this one matches up, and then this one and this one matches up. And eventually, you will have a feature map, right? This feature map is the result of doing the element-wise multiplication as you slide it over, and then adding all the outputs of the result. It's a little bit complex of an operation, but if you sit down and like do it on an example, it's actually simple to understand. But the whole purpose is, like I said before, you're trying to figure out what part of the image has an X, right? If you have a 5, if one of the elements in the feature map has a 5, that means that part of the image probably has it's going to have an X, right? It's going to match up correctly to look like an X. So this whole feature map will tell us, what areas look like it has an X or not. So these areas with 4, right? It's probably this side, and then this side, and then there's a middle part, and then there's a bottom part. That kind of looks like an X, but it's not fully an X. The low values, what means it doesn't look like an X. And so this is just a GIF that's like showing you how it's working. So you have the input data, and you have this like 3x3 feature filter that's sliding across. So that's a window in the light blue, and then right here is the feature map, which is the result. And so this feature map is actually going to be the input for the next layer. And so this is what the filter is. I briefly talked about that you can do an X, right? And you can also do a straight line, but you can do a bunch of other things, right? So on the right-hand side is a bunch of filters that we don't actually specify. Just to repeat again, we don't specify the exact values of these filters. This is actually learned by the convolutional neural network. But this matrix is a bunch of filters that somehow get different images, or different applying pretty much different filters on the images. So like here's a blur, here's a Gaussian blur. You can find edges. Like this one is a pretty good edge representation of the original image, and like you could be able to identify what it looks like. If you had a straight line, right, it'd just be ones down the middle. And yeah, these filters will help us find the features, right? So I'll explain that in later down the slides. But is there any questions about that? Was there anything confusing?
So if the filter was the same size as the input image, then would it just try to find, like before, an X in the middle of the input?
Yeah, pretty much. The reason we don't do that is we kind of want a small filter, because we want to find small features, because eventually using the small features, we can find larger features. And I will show you in a bit. Just let me talk about pooling layer, and I'll explain that in a bit, and then we can revisit if that answers your question.
Okay. Yeah.
But yeah, essentially you could throw a whole filter and it'll cover this, and you can see if it matches X. But obviously, in most cases, when the X is distorted, that won't work, right? Because you have that whole filter and it's covering that input data, and it's not going to match up one-to-one to the original X, the ideal X, because this one's distorted. So this also gives us, just forget that part, but this brings up the question that I talked about earlier. How do we deal with distorted images? And we can deal with this using the so-called pooling layer. So this is the second and final layer that we'll talk about. The pooling layer, its job is to reduce the input size while keeping important parts of the image. So the convolution layer is usually before the pooling layer. And right, we get this feature map. And this feature map will be reduced further using the pooling layer. You could also use the pooling layer before the convolution layer, but it's not common or anything. And in that point, you might as well just resize the image yourself. But that's the whole job. We want to be able to reduce the dimension, reduce the dimension of our input data while keeping the important parts of the image. So this will help us account for shifts in the image. And for example, if we had the 9 here, like, okay, let's say we instead of this max, you can't see me covering this, but instead of doing the max pool, we just map each input data to a neuron, right? So this 9 will trigger one neuron. This 5 will trigger will have its weight with the okay. So let's say there's one neuron, right? This 9 will be hooked up to that neuron. The 5 will be hooked up to neuron, but they have different weights that they will be used in the dot product, right? But if we switch their spots, all right, they're going to still have the same weights, but they'll have a different dot product result, right? Because they're multiplied with different weights. So if we take a max pool, we can see that the max of this bottom right quadrant will be 9, right? And if this 9 was on the most lower right element or spot, it would still be 9 in the max pool. And that's what it's trying to do. If I know, like, it was kind of hard to explain that, but if you want me to, I can write out what I was trying to say in a whiteboard, but if not, I would just continue. So similarly, like before, we have two operands, the input data and this matrix. But instead of a filter, we have this thing called a kernel. This is what all the scientists call it, and this is what they use in like parameter definitions. This is the kernel. It's pretty much a matrix. And we don't specify any values in the matrix, right? Because it's just taking the max of the matrix, right? So we do specify the dimensions of the matrix, right? Here, in this case, is 2 by 2. So we'll have a 2 by 2. We'll take the max of the 2 by 2 on the image, and then we'll slide it over. But instead of doing a stride of 1, we do a full length stride. So we slide the image entirely over, or the kernel entirely over. So that's why they don't overlap like before, where they were overlapping with the convolution operation. So then I'll take the max on here, just slide to the next quadrant, take a max there, and slide it again. So there's actually 2 operations you can do with the pooling layer. You can do the max one and the averaging. So the average would add these all up and divide by 4. Same thing here. But the max is the most popular one. So it usually results in better models when you use the max pooling layer. So here's another a GIF showing what's happening here. You can just kind of see from the GIF like what it's doing. It's just finding the max, and that's why we get this output. And so this is what we call the downsample operation. You downsample the input data to a smaller input data, and we're going to use that smaller input data, right, for the next layers. And this will help reduce computation costs and it helps us deal with those distorted images in that example I said in the previous slide. And so that's the purpose of the max pooling layer. Is there any questions there?
So when we were on the slide that had the different filters, like
Yes. This
like
one.
how do we implement these filters? Because it's because there's a difference between the weights
Mhm.
and then the filters, but then we also have this matrix which we had made from
Yeah.
using one of the matrices.
It is slightly different because we're not doing. It's not like we're doing a dot product like in the multi-layer perceptron, where we'll add the weights to each input data feature and do the dot product across there. This time we're doing an element-wise multiplication. But if you think about it, the filter is essentially a matrix of weights. So instead of having like a vector of weights, which a multi-layer perceptron would do, you have a matrix of weights. And the convolution, like the multi-layer perceptron will learn those weights, right, for the column vectors, right, the weighted column vectors. The convolution neural network will learn the weights for the filters here.
Okay.
So yeah, this is the like a little bit more. This is where it like gets a little complex because like it's still crazy how it learns features because it's able to find the perfect amount of or the perfect filter to use here. So in the examples I described before, where you have like let's say you have a parabola, and let me bring up a slide. So I always show this example when we're trying to train the model. We use a cost function, right? So here we have this cost function, and you have dimensions for the weights, right? So we can find which way or how much to change the weights such that we can reduce the cost or the loss or the error, which is pretty much like the misclassification rate, right? So we want to reduce the misclassification rate, and we can do that by adjusting the weights like this. And so if you think of the filters as a matrix of weights, it's able to do that.
I getcha.
Okay, cool. So was there any questions on the pooling layer? Okay. Yeah. So I would say like the convolution layer is like the more important layer, but I mean, this is obviously important too. But the convolution layer is where it's learning the features, where pooling layer is doing kind of like something to help out with other edge cases and reduce the computation required for the whole entire network. So back to Nick's question, like why can't we just have like, how do we learn the bigger like features, I guess? What if we use like a bigger filter? And let me explain why we use a smaller filter usually. And this is the question of why do we have multiple convolution layers? And these convolution layers are doing feature extraction, right? So what is the point of stacking convolution layers, right? Isn't that just learning features from pretty much a feature map? Like, how does that work out? So let me explain a little bit on the, I guess, motivation and inspiration of the convolution neural network. So I guess a little like history is like the convolution neural network was like built and like before the 2000s, and it got popular by like these three scientists that like won the Turing Award. And they had this idea before there was this other scientist that had the idea of trying to replicate like biology. So like the neocortex, I believe, like they have a bunch of cells, and you have these simple cells that look at the input, right? Just pretty much like whatever you're looking at right now. That's the input, right? And you have these like complex cells that like break down the input. Let me turn my pointer real quick. And it can find like edges and stuff. That's why you can see the edges. It's able to identify the photons coming to your eyes and look at the edge. And based off those edge, we can recreate more like higher level objects, right? So we can, instead of an edge, you have these multiple edges in combination create this corner piece of this, what is this, like a hexagon. So this corner piece of the hexagon, and this corner piece of the hexagon in combination with this one creates the upper part. And upper part and bottom part create the whole hexagon. And this is how our cells are working, actually. So they break down the input data into very small features. And based off these small features, we're able to recreate, higher level features, and then create higher level features, and then be able to identify like this is a hexagon, right? So if you look at your chair or your desk, that's how your cells are working. And this is what we call the neocognitron. And so this is how the convolution layer works. It has, let's say, for example, we have 3 layers, and the first layer is looking at horizontal line, right? So if you had a matrix with ones in the middle, down the middle column, and you had another matrix for looking for vertical or horizontal lines, which is ones down the middle row, and you do the convolution operation, you'll be able to find horizontal lines, vertical lines, right? And that's what the first layer is doing. So the second layer is going to take that feature map from the convolution, the first layer, right? So based off the horizontal and vertical lines, let's do the same thing and look for circles or squares, right? Because pretty much circles are a bunch of small lines, very, very small lines. Squares are 2 horizontal and 2 vertical. And based off the circles and squares, let's see if we can find like floppy ears or like eyes or like legs, higher level objects. So this is why we stack them. Hopefully that makes sense for you guys. And then based off if those regions have like the floppy ears, eyes, and so on, we can throw it in our multi-layer perceptron. I just did a highlight of, this is pretty much a circle, and that's how they build off higher level, low level things build up into higher level things, right? There's pretty much a line and like a diagonal line and stuff. I'm gonna pause there and like answer any question. Oh, by the way, Nick, did that answer your question?
Yeah.
Okay. So yeah, when I'm showing the demonstration, but it's very common to use very small filters. So I'm gonna just recap, just cover everything, just in case like there's any like missing holes. But we have the 2 important layers, right? It's convolution layer and the pooling layer. This one does the element-wise multiplication, and it tries to find those features using that filter. Max pooling tries to reduce the computation, but also try to account for edge cases, like different distorted images that are shifted. Maybe like it was like changed in a slight differently angle or viewed at a slightly different angle. And you have the whole entire process here. We throw in the input data, which is a bunch of pixels. For now, we'll just say they're ones and zeros and n by n dimensions. And you have a bunch of convolution and pooling layers stacked on each other, right? Stacked horizontally. And then they finally connect to the fully connected layer. So, and the whole goal of our convolution and our pooling layers, in addition, there's something I didn't talk about, is the reloops, but they also play an slightly important part in this whole process. And altogether, they do the feature learning. So they find the features based off the image, right? So they pretty much take care of the job of looking at the image and writing down whether that dog or whether that image has upright ears or floppy ears. So this takes care of it. That's how it's all automated. And then you have the classification part, right? This this is going to be able to tell whether it's a dog or cat based off it has floppy ears, upright ears. So this is the multi-layer perceptron. And altogether, this is what we call the convolutional neural network, mostly because it uses a convolution operation, which is feature extraction. On a side note, I will talk about RGB images because nowadays color does like change how the image looks and stuff, because there's like shadows, stuff like that. That's important to take account. But for example, we have this image bunch of colors here. At the end of the day, it's a matrix. Here we can look at the specific red pixel, the red value for that certain pixel, right? Because it might be a 32 by 32 matrix, or sorry, image, but it'll have another dimension. It will have 3 dimensions, one for red, one for green, and one for blue. So here we look at the upper left pixel, and we look at red. So that's a same thing, upper left pixel, we look for green, and then same thing for blue. So that's how RGB images are shown. I'm just going over this is a side note, it's not too important, but we can find the whole RGB value just by looking at these 2 dimensions. And the 3rd dimension really just gives you the specific color. So there was this this resource that I found, and it kind of shows you the whole process of the convolutional neural network. They explain a lot more in detail than what I went into. So if you want to go into it, go ahead. So you can look at like understanding the hyperparameters. So I guess I'll briefly talk about the hyperparameters real quick. So you have the padding, and this padding will change how much you don't, sorry. The padding is like how much of the borders of the input data we don't look at. So like a padding of 1, we don't look at these grayed out borders. We don't even, so like this is not, we don't do an element wise operation here. We'll start it here. So instead of starting there, we start here. So we change the padding, or you can only change it to 1. So I guess that will deal with some edge cases, but kernel size, this is an important one. So this will tell you, the kernel is usually n by n. So if you do a 4x4, it's almost the size of the image, but 3x3 is the common one. And the kernel size that's for the pooling. Sometimes they also call the filters kernels as well, but yeah. And then the stride will tell you how much it's going to move over, right? So if you had a stride of, let me go to a kernel of 1 or 2, and you had a stride of 1, you just move over 1. If you had a stride of 2, okay, I guess it doesn't even let you do that, but there must be some reason. But you can look in that later. And it talks about the ReLU. So if you're really into image recognition, or it does a multitude of things. It can look at like financial data. It can look at like, I think translations. So natural language processing. It can understand like the context of the sentence, and that's because like of its ability to understand spatial features, which is the convolution layer. But it shows you the whole process, so I think it's pretty neat. You can see what it looks like. Like if we look at let's see what's a good image, like maybe this orange. So you can see here, like this filter is able to like identify the brightness, the bright parts of or like the orange shape, kind of. You see here's like it's like a circle. So yeah, that's cool parts. I mean, I know there's probably other images that are probably better. Like maybe like this one can identify this one can identify the actual like liquid in there. I don't know, stuff like that. And maybe this is probably a better one. They can identify like there's coffee in there in that mug. And this one's like identifying the mug shape or something. I don't know, but that's something to check out.
That be in the GitHub page for? Like,
no, that one's on the GitHub page. That one's I put that in the slide. I'm trying to find a slide. Exit full screen. Here I put it in the resources. I should add to more. There is another good video that will help you really understand everything, and it's done by MIT. It's on YouTube. Just look up MIT Convolution Neural Network, and that will show you a video that's like 35 minutes, and it's like it explains everything, math, all like the edge cases, you know, with the distorted images, how it all works. This was just a brief summary of everything. But with that, is there any questions before I move on to the demonstration? Okay, so I'm gonna move on. Quick question for you guys. Do you guys prefer if I like code from scratch, or do you guys prefer a walkthrough? A walkthrough would take less time, but if you want me to code from scratch, it maybe help you guys understand the lines of each line of code.
I mean, I prefer Scratch.
Okay, I can code from scratch.
Go from scratch, please.
Okay, I'll do that. So let me spin up a notebook for you guys. So I'm using Google Colab, which is a similar to Jupyter Notebook. It's Jupyter Notebook, but hosted by Google. So they have servers that have installed very common packages like TensorFlow, PyTorch, scikit, learn pandas, NumPy, which we'll use TensorFlow today. And you can just run Jupyter Notebooks on there, and you don't have to download anything. It's all online. So today we're going to do the image recognition. I did post this in the GitHub repository. So you can go fall 2020 and look in Convolutional Neural Network and go to the Python notebook here and open it in Google Colab using this badge. And I'm just going to code from scratch here. So we're going to be using TensorFlow. So I'm importing the TensorFlow package, and I'm giving it like an alias. So it's called, I'm going to call the entire TensorFlow package as TF. This is what I'm doing here. I'm just going to copy and paste the rest because I don't remember everything from scratch. And quick reference, this entire, well, most of the code on here will be found on TensorFlow's beginner tutorial on the convolutional neural networks. But okay, so same thing here. I'm using TensorFlow.keras, which is how I'm going to specify the models. And I'll use the datasets, layers, and models. And then I'll use matplotlib to plot everything. So I'll use a PLT as the alias. So we're going to run that. And so it just imported the modules, right? You can check if you have the module and like just doing that or something. And so the next step is we want to load the data sets. So if I remember correctly, it's data sets. I don't remember the API, but let me show you guys. You can look at what functions they provide. I think I should do data sets dot. Okay, so like I said, we imported the data sets, which TensorFlow has data sets that they have already provided for you. And they provide the most common ones. So there's Boston Housing, CFAR10, CFAR100, and MNIST, which is like the ones 0 to 9. But we're gonna use CFAR10, which is a bunch of images that are they're classified into 10 different labels. I'll show you those labels in a second. So this one is going to provide a data set. And as you can see here, we can look at some of the source code they have, but they kind of just import that source code from somewhere else. So I have to do .load data. I'm just making sure I'm checking against the thing. Okay, so this thing is going to report back two things: X train, Y train, X test, and Y test. So as I mentioned before, I'm just going to go talk about it here. So you have a training set and a testing set. Testing set is also called the validation set. And the testing set is to test our model or evaluate our model. Our training set will actually train our model, right? So we never use the testing set for training our model, and we never use the training set for testing our model. They will never be used for either process. But our load data will handle that for us. It will split the data, the CFAR10 data, into our training set and test set that we can use. So X train, X labels, and then we have our X test and Y test actually. Let me use train data. Train data, we have train labels and train test data and test labels. I hope that's clear. I'm just going to run it, make sure it's okay. Awesome, it downloads. So one thing I did, or sorry, one thing TensorFlow had told me to do was need to normalize the data. So let me just show you what one of the training data points looks like. As you can see, it's a bunch of values that range from like 0 to 256. That's very common or 255. That's very common because I'm not sure that's how they represent images on a grayscale, probably. But this is RGB, so oh yeah, RGB is 0 to 255. So what they asked to do was to pre-process it and divide each one by 255. So this will help us do exactly that. So I only do it on the train data and the test data, right? The labels itself are going to be, the labels will be either 0 or 1. Sorry, 0 to 9. So 9 being the last class. Okay. So let me show you what the labels look like. So train labels, it will give you a value 0 to 9, one for each class. So if we look at a different train example, it's the last class. I'll explain which classes are in this data set. And now we just did the pre-processing. So I'll show you what the training data now looks like. So before it was a value from 0 to 255. Now we normalize it on a scale to 0 to 1. And this will help a lot with computation. So that's that. So we just did a pre-processing. So as you see here, if you guys are following along here, that's this part. And CFAR10, like I said, is the a data set of 10 image classes. One cool thing is like the best model so far is using a convolutional neural network, and it has 99% accuracy. That's pretty cool. But here are the classes that we were talking about. So there's 10 classes: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. So this whole part, I'm just going to copy and paste this one, is just pretty much plotting the images. This one is not important as the training part. So I'm just looking at 10 images and I am just plotting them. If you want me to explain that part, I can, but that's just plotting stuff. So now the next part is we want to be able to specify the model architecture and then train our model. So let's specify the model architecture. So let's say model equals keras, I think is dot model. I don't remember the API, so I'm gonna check it out. Okay, so we'll do models sequential. So models.sequential is telling us the layers are going to be sequential. So it's going to be processed from left to right. So when we add the layers in, it will know like you need to do this in order. There are other models that like split it up and they run concurrently, but that's like, yeah, that's more advanced. And that's just for like making the training time faster. Sequential is like the normal way to think about a model. So when we do models, the add, we should be able to add what we have here, layers. So we'll look into the layers part of the TensorFlow, and we can look at all the layers here. So as you see, we have a bunch of layers. Like I said, you could do the averaging or max pooling layer. We have average pooling here. And how I did that, I just hit a dot and it brings it up. So you specify the library like directory. So this is layers from TensorFlow.keras. So it's actually looking at TensorFlow.keras.layers. And then I do a dot and I can look at the layers I can use. So I want to use a convolution layer. I think it's 2D. So a 2D layer is pretty much looking at the 2D, only 2 dimensions of the input. But since it's using RGB, we would have like, it should have been 3D, I think, but no, they use 2D here. I can explain that if people have questions, but I'm just gonna move forward. So we can specify the filters size. This is the filter size. We're not specifying the actual filters. Remember, they're learning the filters from the training. So I can do a so filter size, since it's a 2-dimensional convolution layer, we'll do a 3x3. And we'll have that as a filter size. And then you have, oh, sorry. That's the kernel size. Filters is the number of filters. So we'll have 32 filters. So there's going to be 32 neurons in that convolution layer. And they all have a filter of a 3x3. And then so each neuron is hooked up to the red, and is also hooked up to the green, and is also hooked to the blue. And the red, green, and blue, they're all 2-dimensional matrices.
So why 32 for the filters? Why does the filters equal 32?
It's just the number of neurons. We could change it to like 64. Like it's I don't know. It's common to use like something that's a power of 2, but you could do 100. Okay. Right? It's just whatever the scientist wants. And how do you find the most optimal? These are what we call hyperparameters, right?
Yeah.
And how do we find those? We do a bunch of things. You could do like grid search, which it's going to do a brute force and check like every single value that you specify. Like let's say I want to look at 32 filters. I want to look at 64 filters. I want to look at 100 filters. It can do a brute force and check each one. I just did 32 because I don't know. That's what TensorFlow said.
No, I got you.
Yeah, but it will end up in a good model. And then we do the input size because it's the first one, and you need to specify the input size. Input shape here. You can look at the parameter values, by the way. I see here I just went over filters. Oh shit. Filters, kernel size, strides. That's a hyperparameter, not super important. Padding, again, not super important right now. But input size, I think you're supposed to specify it. You're supposed to specify it for the first layer. I don't see here, but do input shape. And it's a 32 by 32 image. So all these images in CFAR10 are 32 by 32, and they're RGB. So there's three extra dimensions, which I did here. I'll do one for the pooling, and then I'll just copy paste the rest. So you do a model.add. Again, we check in the layers. Which layer do we want? We could, scroll through all of them. There's a bunch of layers, but we're going to add a max pooling. So we'll do a 2-dimensional max pooling. So that means that filter is going to be two dimensions, and the pool size. So that's pretty much the kernel size. I believe like 2 by 2 is the one that I did before. 2 by 2. So it's going to have a 2 by 2 max. Kernel that's going to move the slide against the input data and then take the max. So that will be pool size. I know the terminology is like, there's a lot of names for the same thing, but that's just how it is. But the pool size is, yeah, just the matrix size of the kernel. So you can see that you can specify the strides, the padding, but we won't do any of that. If you want to hyper tune your model, you can. Oh, okay. One thing I forgot to do was add the activation layer here. So I'm gonna add the activation function. So before I talked about, there's a bunch of activation functions. ReLU is widely used in convolutional neural networks. So that's right. I'm just gonna use ReLU, and then I'm gonna just copy paste the rest. Right? It's just a bunch of the same thing. Okay, I'm surprised they don't have a max pooling layer after this one. I'm not going to argue against TensorFlow, so I'm just going to do that. We could add a max pooling layer if you wanted to, and that will reduce the input data again. Not a big deal here. This time we're using 64 filters, so there's going to be 64 neurons in this convolution layer. We're going to use the activation is still ReLU, and the filter size will be the same. Yeah, I mean, I could remove this as well, and we could see how it works. And so this is what we call the feature extraction component. Feature extraction layers. Well, it's really just the feature extraction part, because only the convolutional layer does the feature extraction. And then we'll do the classification part. Right, so given all our features from the convolution layers and the pooling layer, we can throw it in our multi-layer perceptron. So we do a model.add, and we'll look at the layers. And like I said before, the multi-layer perceptron is also called a fully connected or dense layer. So dense is what it's called. So units, this is the number of neurons. We're just going to throw 64. In activation, I can do a ReLU like before. And I'm not sure about I should flatten, because remember that the data is 2-dimensional and we flatten it. So let's say a 2-dimensional 4x4 matrix becomes one column vector of 16. So let me draw that out for you guys. So we had, let's say, make it very small. Let's say we had a 2x2. What a flatten does, it's going to flatten our image, not our image, sorry, our input to a column vector of this time a column vector of 4 features, 4 rows. And the reason we do this is this allows our multi-layer perceptron to deal with the data, because it does a dot product, right? So this one is multiplied with W1, this one's W2, W3, and W4. And like it's just a little bit harder to do it with the matrix. So this simplifies things for the multi-layer perceptron. So we don't change anything in the multi-layer perceptron, right? We just add a flattening layer. So you do a layers.flatten, I believe. I don't remember how I did. Yep, layers.flatten. And then, so we have one hidden layer. And we have our, we could add another hidden layer, but I'm just gonna go ahead and add the final layer for predicting the 10 classes. So we'll add another dense one, which is another multi-layer perceptron with 10. I chose 10 because it's a number of classes. If we had one class we're trying to specify or predict, like whether this image was a dog, then we would just have one output. So we'll throw in a redo in there as well. Output layer with 10 nodes for each class, 10 neurons. Okay, so that's our model, and let's look at our summary. Is there any questions on like the code there? Or are you guys good? All right, so this is just a summary of everything we have. We have 2 convolution and pooling layers, and our flatten. We flattened the 2-dimensional into a 1-dimensional input data so that a multi-layer perceptron can easily read that. And then we output into 10 neurons. Each neuron is going to tell us, is it part of our class or not? Okay, so another thing. So now we're going to train it. So do a model.train. And hopefully it tells me the parameters. I don't remember it off my head. Model.compile. Okay. So you do a model.compile, and this will tell you the configuration of what we need to, how we're gonna, what optimizer we're gonna use, and what loss function we're gonna use. And I believe the third one is like, what are the metrics we're going to train to optimize? Actually, no. This is just extra for us to evaluate our model later. But the really 2 important parts are the optimizer and loss function. I've never really talked about the optimizer, but gradient descent is the very basic one. Everything is just a more complex gradient descent. So you can use atom or stochastic gradient descent. They are better than gradient descent just because they've been like tuned by scientists. And then we have our loss function. I'm using a cross entropy, which is a very complex loss function. It's not super complex, but it's not your typical mean absolute error or your mean squared error. This one is just trying to find the difference in probabilities for 2 different distributions. Like one distribution can be dog, another can be cat, and it's trying to figure out like whether it's in this distribution or not. I'm not going to go too deep into it actually. So we're going to go into chars.losses, and then so I just specified I'm going to look at TensorFlow and then keras, and then we're going to look at the loss functions. So if we Googled this, we could find the API for this. So TensorFlow has documentation for this. So if you ever get stuck, just look into the documentation. So here on the left-hand side is a bunch of the losses. I just mentioned the mean squared error, mean absolute error. There's a bunch of different ones. We're using cross entropy because it's very, very popular to use. And then from logits, I think this is should be, we don't need to specify. Oh, from logits, true. Okay. I haven't explained logits, and I probably won't. But if you have a question, I can explain that. But and then metrics. Let's make it look nice a little bit. So metrics equals, we want accuracy. So we can have accuracy, we can have a bunch of other stuff like precision. We'll just stick with accuracy. So we'll compile that, and then we'll do train. So this one is just configuring our model for training. And then this is actually training our model. This is doing the, if you remember from the multi-layer perceptron, this is where it's going to run a bunch of data points through our model and test like whether it correctly predicted or not. And then it'll change the weights based off that cost function. So it's model.fit. Okay. And we can look at the parameters. So you need to specify the X values, and then you specify the Y. So X is our train images, and then we have train labels. Batch size, that's not something I've covered, but that'll tell you how many data points are in a batch. Epochs is the number of how many times is a total number of times we've gone through the entire data training set. So if we do 10 epochs, that means we went through the entire training set 10 times. Validation data. So this is how we're going to evaluate our model. So every epoch, we're going to look at our validation training, our testing set. And this one is our test images, test data, and our test labels. Train data. Now we're run. So that will take some time to compute. So I will just skip over to this notebook here. I'll zoom out. So as you see, we had 15 epochs. So that means we went through the entire training set 15 times and trained the model each time. So the next epoch, we still use the same trained model from the last epoch. So near the end of the training process, we should have a better model, like a much better model, right? So you could train it like 100 epochs and it should be very good. But here's one thing. One thing is this idea of overfitting. So you have this blue line and then you have this orange line. This orange line is our validation accuracy. Our validation accuracy is the percentage of data points that are correctly classified in our validation set. So that's our testing set. So that is not used for training, and that is just to help us evaluate whether our model is doing good or not. So you can see it kind of stagnates, but our accuracy, which is the proportion of data points that were correctly classified on our training set, it keeps going up. So that's when you know it's starting to overfit, because it's overfitting to the model is overfitting towards the training set. But we just wanted to like have it stop here, right? We don't want to overfit too much, because if you overfit too much, sometimes your accuracy like tanks. Here it doesn't. So I mean, it's not the end of the world. It's still going to train, so I just have to let it train. Here, like this is the less important part, because we just went through the training and the architecture. So like here wasn't that much code. Most of the code, yeah.
So just before training the model, like I'll be honest with you, I missed that that section, because at the time my mom had called me down. So
no
she needed help with something. So
this one right here, the one I have highlighted.
Yeah.
Okay. So I'm gonna go back to our notebook from scratch. So after the feature extraction part, I started adding the multi-layer perceptron. So one thing that is new is the flatten layer. So with the flatten layer, what it does, it takes our two-dimensional input data from the feature extraction part, right? Because they're all working in 2 dimensions. That's how images are usually 2 dimensions.
Yeah.
And it flattens it, so our multi-layer perceptron can like do its thing, where it does the dot product, right? I mean, like we could have this point to do the dot product with a W1 and then W2, W3, W4, but it's just much easier to flatten it. So we just convert this 2-dimensional data to a 1-dimensional row vector or column vector.
All right.
And you don't really specify anything. It just flattens it. So it pretty much like stacks it vertically. And then you have our dense layers, which is the multi-layer perceptron hidden layer. And we specify 64 neurons using a ReLU. Very important part is to use a ReLU. If you use another one, like a logistic activation layer, it usually doesn't do well.
Did we already say
that in the previous meeting?
Did we already state what what the ReLU activation did?
So the ReLU activation function, it pretty much throws. So you remember how the multi-layer perceptron, it does the dot product, right?
Yeah.
And based off that result of the dot product, we throw it into this activation function, right? So if the dot product had a value of 0, it's going to stay 0. Or sorry, negative. If it has a value that's negative, it'll stay 0. So if the dot product end up being -2, when you throw in the ReLU, it's going to be 0. Whereas if it's positive, then it's going to remain its own its identity. It's going to remain 3 if it's 3.
And does it also depend on, like, I imagine that if if the value is less than 0, then does it stay below? Like,
It's
trying to think.
So think of this as, think of the x-axis as the dot product result, right? So if it's negative, it's just going to be 0. So it helps with a couple.
Okay.
Yeah.
So like when so if the value is at 3, then the ReLU activation would give that weight as a 3.
Yeah, it will give 3. Mm-hmm.
Yeah. All right.
And I guess this is a side note, but it just helps with a problem called diminishing gradient problem. But that's like an off note, and it gives you better accuracies usually. So that's why ReLU is more popular. But the next layer is our output layer, and we have 10 neurons, 1 for each class, and that's it. These end up spitting what we call logits, but don't worry about that. I'll show you in our notebook here that I provided for you guys. I'll explain everything in a second. But this one, I just went over the model performance, and this is using matplotlib to plot it. So I'm plotting just the values, the accuracy values and the validation accuracy values. Yeah, and we do a model.evaluate. So this is, I guess, another important function call here. So we did a model.fit, which is the training, fitting to our training data. But we want to evaluate on external non-training data. We use we want to evaluate on our testing data, right?
Yeah.
So this is our validation set, and we use model.evaluate.
And what was the main difference between the accuracy and the value accuracy?
Yes. So val accuracy is
for
validation. Yeah, you got it?
Yeah.
Okay, cool. Then I'll just move on. So this one is a little extra. This one is like, let's see what happens when we use an image to find on Google. I don't know. I'm not sure if you guys are really interested in this stuff, but this is just using some of like Python's capabilities of like, you can create stuff really fast with Python. This is why I like it a lot. And it's really, the machine learning like libraries are heavily built and rely on Python most of the time because it's so fast. Here I do build another model, and this is what we call a probability model. This will tell us the probability that a data point is in which class. So we just add a softmax layer. So let me just show you guys what a softmax is real quick, because it's kind of used everywhere. It's pretty much just finds a probability, right? So it's like, yeah, just think of it as finding the probability. I'm not going to explain the math into it. But this is something you learn in like machine learning class. And this part, I just pretty much find an image. So we find an image of, what are the classes here? Let's try to find an image of a dog. And let's see if our model works. So we copy the image address. Hopefully I don't have to run this again, because then it won't work. But hoping it works. Oh, okay. Well, dang. Let's see if my model finished training. So it's almost done. But how this would work is it would pretty much download the image and throw it into our convolution neural network, and it will tell us what class it is. So before it was it was able to tell us a horse. Let me leave this page real quick. Hopefully it saved this stuff on the bottom. Okay, so here I found an image of a horse. I legit just like Googled horse, and then I found like some image of the horse. Like it was probably this one or something. And then actually it was one of these. And then I resize it to the same size as a CFAR10 input data, 32 by 32. And then as you see, it's really small here, and it tells you what it is, and it's a horse. So yeah, that's it. Any questions there? Okay, I'm going to stop sharing. Let me stop recording first.